From the previous video, I had implemented a 4x4 unsigned multiplier using the IP packages provided by Quartus. So I used their multiplier, basically LPM underscore mul, which is a multiplier block that has been provided. So yeah, using that, now instead of displaying the binary value of the multiplication on the LEDs of the FPGA, now I'll be displaying the same result onto the 7 segment displays that you can see on your board. So how would I go on about this? As you can see, the first block would be a multiplier block. As I explained from the previous video, this is a 4x4 unsigned multiplier, so the output would be 8 bits and the width of A and B would be 4 bits, and these are the these are the other pins that are available, that are provided by this LPM mult module. So the first step would be to generate or to code the 7 segment display. So for reference, let me just show you how it would look. So for reference, this is how a 7 segment on a DE1-soc board would look. So here are the pins. This for each there are 6 of this, and for each of this pin has to be coded. So since this board is an active low board, which means when you put a 0 or when you ground a particular point, it turns on. So that is what is being done here. I've coded the digit and a segment. So the segment would be each of this. As you can see, there are 7 bits over here, 0 to 6. So these are the bits, and this is the digit. So for if I want to display a 0 on the 7th segment, uh, as you can see, all the other only the 7th bit is 1 and all the other bits are 0. So practically what that would mean is, since all these bits are 0, this would turn on except for the 6th bit. And as you can see, similarly for 1, you only want 1 and 2 to turn on, so the 1 and 2 are coded to be 0 and the other bits are coded to be 1. Similarly, as you can see, I've coded all the bits since it's an active low. Let me go ahead and to the next part. So having done that, you'll be multiplying uh, 4 bits, right? 4 into 4 bits. So as you know that the maximum value from 4 bits that you could get is 15. So in the sense, if you calculate 15 by 15, 15 into 15, that is 225. So the maximum value that you could get is 225. So there is a hundreds, tens and a unit place that you'll have to extract. So this is what it does. It basically extracts the tens, hundreds, tens and units place digits or the value. So what it does is, it takes the value, it takes the input from the result of that multiplication and then outputs the hundreds, tens and the units. As you can see, since it's 225, 0 to 2, you divide it by 100. So this, what this gives is, this gives the the quotient. So you would extract that 10 the hundreds place, and to extract the tens place, you would mod it by 100. So basically you'd get a remainder, and that remainder is divided by 10, so you'd get the quotient here. Now what do you do for to extract the units place? You'd basically use the modulus function on 10 by 10, so there you get the extract the last place. So if I were to take the example of 225, so 225 by 100, so since this would give quotient, so 225 by 100 would be 2, so this is what you'd get here. And again, since I'm taking 225, mod of 100 would mean that 225 divided by 100, that would give you 25, since modulus returns the remainder, and 25 by 10 would be 2. So that's how you'd extract the tens place. And again, 225 modulus 10 would give you the remainder of so 225 by 10 would be 22. So having taken out 22, 220, you'd get the 5 as the resultant. So that's how you'd extract the unit place. So this basically extracts the hundreds, tens and the unit place values. You could question that I've used directly 100 and not converted the binary to BCD, and then I'm dividing the BCD value by 100. But the case here is, since you give it as 100 already, this the program would read it in binary. So whatever the value that you would get, even if you're using 15, it even if your result is 15, it will be coded as it'll take four ones, and the 100 will be converted into its consequent binary form and divided, and that operation will be done. So that's how you get your 100 tenths and unit place. Now, having had these two modules, we'll generate a new module where we'll call it all together. So here are the two inputs. I've also used the clock, and these are the six segments available on the board. Now I've used these two as the reg and a wire to store the values, and this is for hundreds, tenths, and unit place to call it in the BCD program. So what I've done here is I've called in the multiply block, and I've coded data A for A of this, B of this, and resultant wire of this. Basically, I'm mapping what are the inputs and outputs of that program to this program, and I will use the clock for calculation, or to find out the calculation or the fmax purpose. And then I've used this to as I said, to extract the BCD values, the hundreds, tenths, and unit place, and then I'm sending these values to the hex 2, hex 1, and hex 0, basically the rightmost corner 3 bits, or the 3 7 segment displays, and I've hard coded this so that they don't turn on the other 3 LED bits that we are not using. So this is the program. I've already gone ahead and compiled this program. Let us see the resources being used here. As you can see, all the reports 97. Having done the packaging, you could save two of those ALMs by tightly packing it together, or after many optimizations. So hence it would be 95, and the number of ALUTs being used is 187. Now there are 51 pins being used. It's very high because since I've coded other LEDs, also hard coded the other 7 segment displays, so that will also be considered as pins, so that's why it shows high usage of pins. The number of TSP blocks used is 0, and the BRAM, or the memory, no, the memory used is 0. Memory on the board used here is 0. So let's go ahead and look at how it would look and be implemented. Here is the RTL view. As you can see, there are 3 blocks. This is the multiplier, this is the 7 segment display, and this is the code for the 7 segment, and this is binary, the converter, and then the 3 7 segment displays being used are shown here. As you can see, 5, 4, and 3 are hard coded to be left hanging. Now let's at the same time look at the chip planner. This is post fitting. You can see it's pretty much the same thing. It just shows how it's been implemented on the FPGA. Now we could again go ahead and look at how this whole thing is being implemented on the chip. As you can see, this is the chip as I explained. Now the chip, the FPGA board. So as you can see, this part is marked here, which means that our program is being implemented in these 3 blocks. So let us go ahead and check one of the blocks. You can see it shows how the program is mapped onto the FPGA based on the Cyclone 5 architecture. So here, if you could zoom in, you could see all the details you'd want. Similarly, you can see it's been hard coded here in around these blocks. Now the test bench would be same as the other one, so I'll be directly showing the implementation onto the FPGA board. Let us go ahead and program our FPGA board. I've already pre-programmed the pins to be used on the FPGA. This is a family of boards that we are using. So Let us dump the file that we'll be using. The dot is a file which contains the bit stream. As you can see, it's successfully done. Now I'll be showing the outputs on the FPGA. Thank you.
Already explained, I've dumped the program onto the FPGA. Now let us do a few test runs. Now let us do 3 into 5 as shown in the test bench before. This would be your A, this would be your B. As you can see, it's 3 into 5, 15. Let us do 7 into 9, 7. As you can see, it's 7 into 5, 35. I'm making 7 into 9. As you can see, it's been shown as 63. Now let us do the 15 into 15 to check if it actually works. As you can see, it shows 225. We can also use the LEDs to do the same. It's just that in the main module we'll just have to include another block called another definition called result as output, and then send that result that we have got from the multiplication to that newly defined variable called output, so you can actually have the display showing the BCD form and the binary form of the multiplication. So that is another implementation that could be done easily. Thank you.